Hello everyone, I'm Vismaya Rajeevan and I'll be talking about one of my work, Structural and Magnetic Properties of Chemically Synthesized Iron-Based Ternary Alloys. As we all know, iron cobalt alloys possess superior magnetic properties like high saturation magnetization, high Curie temperature, low coercivity, and low magnetocrystalline anisotropy. It makes them desirable for various applications like high efficiency power applications, microwave absorption, magnetostrictive transducers, etc. But one of the drawbacks with iron cobalt alloys is that it is expensive comparing to other ferrites and irons due to the presence of cobalt. Also, low corrosion resistance and brittleness increase the cost of practical devices due to additional anti-corrosion steps and difficulty with machining. These disadvantages could be circumvented to some extent by using nickel addition to the iron cobalt system. From the figure, we can see that iron cobalt is having the highest saturation magnetization and low coercivity, whereas iron nickel is having moderate saturation magnetization and lesser coercivity. Thus, adding nickel to the iron cobalt system may result in desirable magnetic properties. Iron-based alloys could be synthesized through various synthesis techniques like ball milling, thermal decomposition, hydrogen plasma metal reaction, etc. But they have disadvantages like agglomeration, strain-induced effects, prolonged synthesis duration, difficulty with composition control, etc. Thus, we have used polyol process as a synthesis technique, which is an instant chemical reduction technique and is a much simpler, faster, cost-effective and eco-friendly technique that is used to obtain non-equilibrium phases. We have used the precursors iron chloride tetrahydrate, cobalt acetate tetrahydrate, nickel acetate tetrahydrate and introduced them to the solvent ethylene glycol at an elevated temperature of 180 degrees Celsius. NaOH pellets are also used to facilitate the reduction. Unlike the conventional polyol process, which implements refluxing, here we have used a one-pot, one-step polyol process. Here we have synthesized iron 40 cobalt 60, iron 40 cobalt 53 nickel 7, iron 40 cobalt 50 nickel 10 and iron 40 cobalt 46 nickel 14. From the XRD pattern we can see that it exhibits BCC phase for all the compositions in accordance with the equilibrium alloy. The ternary iron cobalt nickel system usually presents the FCC phase with higher cobalt even with nickel as low as 5 atomic percent. Previous reports suggest that single-phase iron cobalt nickel BCC alloy was difficult to achieve due to the mismatch in the reduction potential of iron, cobalt and nickel. The formation of BCC iron cobalt nickel alloy here in our studies is facilitated by the rapid introduction of precursors at an elevated temperature that helps in the easy nucleation of BCC iron. The lattice parameter of iron 40 cobalt 60 is calculated to be 2.855 angstrom, which is incompatible with the literature value. For the iron cobalt nickel alloys, the lattice parameter value decreases up to x equal to 7 and then increases with x equal to 14, indicating random local substitutions of nickel in the BCC iron cobalt phase. The sim images of the sample shows that the morphology of all the samples is spherical, with an average particle size decreasing from 210 nanometer to 155 nanometer on increasing the nickel concentration from 7 to 14 atomic percent. Here the nucleation of the particles takes place for a shorter period favoring the growth stage, thus leading to a larger particle size in the range of 150 to 250 nanometer. The diameter of iron cobalt nickel particles decreases with increasing nickel concentration due to the stronger reducing ability of nickel in polyols. The average particle size is much higher than the average grain size obtained from the XRD data, suggesting the sample's polycrystalline nature. The TEM images shows the presence of an amorphous layer both for iron cobalt and the nickel substituted alloy. The figure shows the room temperature hysteresis loops for the iron cobalt and iron cobalt nickel alloys. The as synthesized iron 40 cobalt 60 shows a saturation magnetization of 152 EMU per gram, which decreases with nickel substitution, reaching 118 EMU per gram and increases further to 129 EMU per gram and 155 EMU per gram with 10 and 14 atomic percent of nickel. As the saturation magnetization is affected by the presence of secondary phases and the maximum applied field, the quantification of saturation magnetization with the iron cobalt nickel is difficult. The nickel addition alters the electron density of states, resulting in varying saturation magnetization. The coercivity decreases from 157 to 96 on increasing the nickel concentration from 7 to 14 atomic percent. The magnetocrystalline anisotropy of iron nickel is lower than that of iron cobalt alloy, and it suggests the reduction due to nickel addition. The figure shows the thermomagnetic analysis of iron cobalt and iron cobalt nickel alloys. The iron 40 cobalt 60 shows a Curie temperature of 1010 degrees Celsius influenced by phase segregation, which drastically reducing to 840 degrees Celsius with 7 atomic percent of nickel. With further increasing nickel concentration, the Curie temperature reduces to 810 and 760 degrees Celsius. The reduction in Curie temperature with increasing nickel addition refers to more nickel neighbors and indicates the formation of iron cobalt nickel alloy. The presence of amorphous phase may also contribute to the reduction in Tc and its distribution. The compositional dependence of Curie temperature of a ternary alloy has been expressed by this cubic equation. It depends on the atomic concentrations of the elements, Boltzmann constant, Curie temperature, and spin-dependent coupling coefficient. The spin-dependent coupling coefficients are the function of exchange energy, kinetic energy, and nearest neighbor contributions. Iron cobalt nickel exhibits several atomic interactions, namely iron-iron, iron-cobalt, iron-nickel, cobalt-cobalt, cobalt-nickel, and nickel-nickel, and this influences the exchange in kinetic energies, which in turn reflects in the Curie temperature. Previous works have reported that iron-cobalt exchange interactions are much stronger than iron-iron and cobalt-cobalt interaction. For example, Isidar et al. Have reported weaker iron-nickel and nickel-nickel interaction compared to iron-iron interactions in Elton-ordered iron-nickel. Similarly, Budko et al. Have reported a significant decrease in the average exchange integral in cobalt-nickel alloys, with a gradual increase in nickel concentration suggesting weaker cobalt-nickel interaction. So the addition of nickel to the iron-cobalt system may lead to the formation of new interactions which are weaker, and this decreases the average exchange interaction. As Curie temperature can be determined by the average exchange interaction, the nickel addition leads to a Curie temperature that lies between iron and iron-cobalt. The magnetic properties of iron-cobalt and iron-cobalt nickel alloys are tabulated here. Next, we are talking about magnetocrystalline anisotropy. It's an intrinsic magnetic parameter and can be obtained from the analysis of MH curves based on the law of approach to saturation. Here we have used modified law of approach to saturation given by the equation m of h is equal to ms into 1 minus a by h minus b by h square minus a by root h. This figure shows how well the experimental MH curves fit with the law of approach to saturation for all the samples. The cobalt-rich iron cobalt shows a high K value of 33 kJ per meter cube, which may arise due to the intrinsic anisotropy of the iron cobalt system and other anisotropies such as interfacial and stress anisotropy. The K value decreases with nickel substitution, nearly around 10 kJ per meter cube. The presence of amorphous phase may also facilitate the soft magnetic nature, which results in the averaging of magnetic anisotropies. The corrosivity is directly proportional to the magnetocrystalline anisotropy. Nickel substitution is expected to decrease the corrosivity as the alloy becomes more soft magnetic due to the reduced magnetocrystalline anisotropy. The particle size effect may also impact corrosivity. Hence, the competition between particle size effect and the magnetocrystalline anisotropy leads to corrosivity fluctuation, while it is the least for largest nickel concentration. Thus, we have calculated critical superparamagnetic size and critical single domain size. The magnetic parameters obtained for iron cobalt nickel alloys from the LAS are tabulated here. The calculated critical superparamagnetic size for iron cobalt and iron cobalt nickel alloys are in the range of 18 to 22 nanometer. Since the average particle size of all the samples are far larger, iron cobalt nickel alloys are not in the superparamagnetic regime. Similarly, critical single domain size are also much smaller than the average particle size. It implies the existence of multi-domain structure. Since all the particles are much above the critical single domain size, the variation in corrosivity with nickel substitution may arise from the particle size distribution and pinning effects in the multi-domain iron cobalt nickel. So we can conclude that nickel substitution could result in better soft magnetic properties. This is the summary of my work. With this slide, I am concluding my presentation. Thank you for listening.